Our first speaker of the day is Jon Kleinberg. Jon Kleinberg is the Tisch University Professor in the Department of Computer Science and Information Science at Cornell. His research focuses on the interaction of algorithms and networks, the role they play in large-scale social and information sciences, and their broader societal implications. He's a member of National Academy of Sciences and National Academy of Engineering. He's a recipient of MacArthur, Packard, Simon, Sloan, and Vannevar Bush fellowships, as well as Harvey Prize, Nevanlinna Prize, and the Prize in Computing. He has done, after reading this, it's clear that he's done tremendous work at the interface of social sciences and computation. And I look forward to his talk on consensus and discord in model of opinion formation. All right, with that, handing over to you, Jon.
Thanks very much. Thanks very much for the invitation to take part in this event, which is extremely interesting, extremely timely, and of course brings together a set of topics that have common methodological underpinnings, but obviously are very much on people's minds in different spheres of society. Obviously, in the realm of disease and epidemics, and also in the realm of information and misinformation, and the way these things spread through society. And trying to look for both the commonalities and differences in these topics is, I think, an extremely interesting undertaking. The talk that I'll be giving here is going to be motivated by the spread of information, and in particular motivated by models of opinion formation. And this word "models" in the title is key in that this talk will definitely be grounded on the theoretical side. It will invoke empirical work that people have done, some of which I've been involved in, a lot of which is just going on throughout the community. But it'll sort of be informed by that, but it'll focus in this particular hour on some of the theoretical questions. So, and I'll be covering a combination of papers here with the co-authors that I have here on the title slide. I'll be mentioning some of the papers by us and by other groups as I go along. Okay, so if we're going to talk about opinion formation, it's useful to think about how much networks and network connections play a role in the way we experience opinions and information, right? So I thought it might be useful to start with this headline, which is actually about 5 years ago, about 5 years ago, as the 2016 election was coming up, as we were in the primary season for that. It was an open letter to Matt Taibbi of Rolling Stone magazine. It's a brilliant response from a millennial to Matt Taibbi's displeasure over Rolling Stone's endorsement of Hillary Clinton. Now, the reason I mention this is actually not to talk about the content of what any of these people thought, but to sort of observe how, sort of at a meta level, how many layers are represented in that sentence and how much your brain has to process, right? How much sort of cognitive work you have to do in order to unravel what this second subtitle of the headline is actually saying, right? If we were to draw it out in network form, it's relatively complicated, right? So someone has an opinion on Hillary Clinton. Who is that? It's Rolling Stone magazine because they endorsed her. Someone had an opinion on that. That was Matt Taibbi, who actually writes for Rolling Stone, who apparently was not happy with this endorsement. Then a millennial apparently had a brilliant response to Matt Taibbi's view on what Rolling Stone thought of Hillary Clinton. But it didn't end there, because in case you didn't see this millennial, this website decided to highlight it. And this website apparently, because it calls it brilliant, seems to like the response the millennial had to Matt Taibbi's response to Rolling Stone's opinion about Hillary Clinton. And the funny thing is, when you say it that way, when you trace out these links, it sounds very complicated, because at some latent level, it is complicated. On the other hand, we read through sentences like this on the internet all the time, and we often don't notice the cognitive work that we're doing to actually, in a sense, map out that network in our head. I would argue anyone who actually read that sentence had some version of this representation as they were doing it. And of course, it doesn't stop there. I mean, I chose this as an example, and you presumably have some opinion of my choice of this as an example. And if you were to, for example, relay this whole story to somebody later today after this talk, then you would have added one more link onto the chain, because they would have some opinion of you telling them this story. Okay, so 6, 7 degrees of separation in the space of opinions and information is something that we all are able to handle. And it sort of squarely situates why it seems natural that network models might be relevant to what we're talking about. Now, of course, there's a long history of how opinions spread through social networks, through mechanisms like the one on the previous slide. In 2004, at a workshop not unlike this one about contagion information, although unlike this one, it was in person. In 2004, I had the good fortune to meet the first author of this book, Personal Influence, Ella Katz, 50 years after it was published. And we had a very interesting conversation about the different ways in which trying to understand disruptive technologies had shown up at different parts of our own professional careers. In his case, early in his career, it was the emergence of TV and its impact on the political process. And in the case, in my case, and those of all of my colleagues, it's been the internet, it's been blogging, it's been social media. So, but with all these technologies, we find that the technology is not really directly transmitting the opinion to everybody. It drops the opinion into social networks that are still even now made up of people, and the opinion spreads in that way, right? When people were asked what had contributed to their decision, as they wrote in their book, their answer was other people. Now, because of this, a large number of models have been proposed for how information might spread in networks. And my goal in the next 40 minutes or so is to walk through some of these categories of models, talk about some of the results that it's possible to obtain here, again, with an emphasis on the theoretical dimensions and to sort of think about what these might say about the systems that we work with. Here are 3 large categories of models that, in a sense, have evolved somewhat independently. Overlapping people work in each of these areas, but I think actually one of the questions in this whole field is to find deeper linkages among these different strands, and there certainly are some. The first, which I won't be talking about really in this talk, is to employ probabilistic models, to say that an opinion is some sort of a conditional probability that you have in your mind based on information you've observed. As you talk to other people, that gives you new information, and if you condition on that, it should shift your probabilities using Bayes' rule. And so a large body of work has engaged in the kind of calculations that you would have to do if you ask how would an agent in a network receiving information across the links of the network update its beliefs in this Bayesian way. A big challenge here is that the calculations get really, I think it's fair to say, extremely complicated, and that raises sort of 2 concerns. One is that it's hard to work out. It's hard to answer even some basic questions in this area. And second, it's also, of course, hard to imagine that human beings in the network are engaging in such difficult calculations if it's even hard to do them in order to write the paper. A second one is a much more basic kind of process, which is a sort of weighted averaging process, which you can motivate in some sense by a kind of naive take on probability. You can also motivate just by some notion of sort of subjective naturalness, that each agent has an opinion which is given by some real number. Its neighbors in the network have some real number also, right? So the real number could be, where are you in the political spectrum? Or, how strongly do you support this political position? Or how much money should we spend on education in our school district, right? Some real valued number. And your neighbors have numbers, and in each step you update your opinion as some kind of a weighted average of your own opinion and your neighbor's opinions. It doesn't have to be a uniform weighted average, but it's this kind of aggregation that treats this very mechanistically. If I contrast this with the first style of work, it has the advantage that it's much easier to work with. It arguably looks more like what people might be doing. On the other hand, it of course is subject to the criticism that it's less well grounded in first principles of agent level reasoning, as in we essentially are at some level arbitrarily making up rules and arguing for their naturalness. And in the end, there isn't a resolution at the moment of either of these concerns, either the ad hoc nature of some of the models, nor the difficulty of using ones that are probabilistically grounded. But I think it's informed a lot, and in fact that tension I think has informed a lot of the work in the area. Again, some of which I'll hint at in the talk, but which goes much deeper as well. A third issue, which I'll actually come back to in the final 1/3 of the talk, is that so far I've really been talking about opinions as things that are residing on nodes. A node has an opinion, the node updates their opinion. But you can also think about something like opinions, certainly something affective or subjective, as existing on the pairwise relations between agents, right? So if I get along with one person and don't get along with another, if one person is my friend, one person is my enemy, these are all statements about not me or them, but about the pairwise relation between us. And so it would be natural to also put some kind of a weight or some kind of a number there to indicate positive or negative valence in our relations. This goes back to a very long, very deep line of work in sociology and social psychology called structural balance, which again I'll come to as I move on in the talk. Okay, so but let's start by talking about weighted averaging. And as I said, the simplest models here, and probably the most basic model, is something which has been independently proposed a number of times. It's often called the de Groot model, after one of those independent formulations of it by de Groot in 1974. Each node has some value x sub I. And in each time step, time moves in discrete steps, it's going to update its view as a weighted average of xi and the xj of its neighbors. Okay, so just xi gets updated to be this weighted sum, and there might be weights on the edges, for example. Okay, and I should say that there's a question about how minimal we want to make the assumptions on the graph. Could the graph be directed versus undirected? Is the graph connected? Does the graph have periodicities in it? And since I want to sort of keep some of those in the background for this particular talk, although some of them get interesting, I'll focus here on connected undirected graphs, where most of those concerns don't tend to come to the surface. Okay, so in such graphs, connected undirected graphs, this looks somewhat like a Markov chain update rule, and theorems from that area will tell you that in this case, positive edge weights, connected undirected graph, the process is going to converge to a consensus. All the xi's are going to be converging to the same value, right? So if I think about this simple example down here, where we just have a 3-node path, 0, half, and 1, in one step of iteration, this half is kind of anchored between the 0 and 1. So by symmetry, it's kind of stuck. But the 0 will increase to 1/4, the 1 will come down to 3/4, and obviously on this extremely simple graph, you see how everything is collapsing to the 1/2 in the middle. So an interesting question here is that this model, and many variations on it, we can change it in a lot of different ways. We can change how the dynamics operate. All of them seem to be sort of following this gradient toward consensus, that everyone agrees on the same value. And so it becomes natural to ask, often what animates us in these questions is the many situations where consensus is not reached, where there's either, a spread of opinions in the network, there's potentially polarization, things where we're not all arriving at the same numerical value for what we think, where we lie upon the spectrum on which we're disagreeing. So what do we need to add to the model, preserving its simplicity, right? It's sort of essential basic simplicity here. What would we have to add to it in order to have something which does not arrive at consensus? And one very elegant proposal here, which is now from 1990, is this model of Friedkin and Johnson. There are a lot of ways to describe the Friedkin-Johnson model, so I'll pick a particular way of describing it. So it says, let's again take this network where each node has a number, which is their opinion. But let's think of that as an expressed opinion, Z sub I. Let's imagine each node also has some sort of innate or internal opinion, S sub I. So instead of the picture on the left, which we had on the last slide, let's think about the picture on the right, right? So we have these 3 nodes, U, V, and W, and the circle is their expressed opinion, what they share with the world. But in these squares, in the background, is their innate opinion. And that, crucially, does not change through the iterations of the algorithm, okay? So what happens here? So we again have an update rule. It's again a weighted average, but it's a weighted average of your neighbor's expressed opinions and your own innate opinion, okay? So in every step. So, for example, you'll notice that I've sort of jumped ahead a bit in this picture. and draw on a configuration of expressed opinions that actually is stable relative to this update rule. Because when node U goes to update, it averages the half expressed by its neighbor V, its unique neighbor V, and the 0, that's its own innate opinion, that gets a quarter. V similarly is averaging the 1/4, the half, and the 3/4. W is averaging the half and the 1, and they regenerate these values. Okay, so this is a fixed point of that particular dynamics. Now, I should mention that I'm describing this as an averaging process. If you want, you can describe it as a cost minimization process also. So at the bottom of this slide, I've drawn for you a cost function that's, again, quite natural, that we could think of, in fact, the averaging as minimizing. The cost function is based on some internal stress between the opinion you're expressing and your innate opinion, which we measure as a quadratic function of the distance between them, plus tension along the edges, right? When you disagree with one of your neighbors, because we're going to assume a sort of motivation to engage in harmony with neighbors. When you experience differences with neighbors, we get some tension, Zi minus Zj squared, weighted by the strength of that connection. Okay, if node I were to do a kind of best response dynamics and select a Zi to minimize this cost function, taking everything else as fixed, it would do this weighted averaging step. Okay, so we could also think of this as a kind of local search towards some kind of a local per node cost minimization. And there's a fact here that repeated updates converge to an equilibrium, but it need not be consensus, as it isn't, for example, in this case. There's a question of what the innate opinions actually correspond to here. And in some sense, the flexibility of these theoretical models means we can make various choices. You can certainly either think of this as trying to capture something about this is your innate set of beliefs that are not affected by social influence from neighbors, and it persists throughout the process. You can also think of it as it's some information source you have access to that's unchanging. And so every time you go to update based on new information, you continue to consult this unchanging information source. Right, so in some sense that sort of makes it something that exists outside of you rather than internally to you. And that either of these is a potential interpretation of what this model mathematically is doing. Okay, so here are a few basic facts. I'll just show you a few basic facts about this model, and then actually it's in the spirit of pausing every 15 minutes or so to check for questions, I'll pause after the next slide. So this is the cost function that the agent is locally minimizing. So the equilibrium, if they're repeatedly locally minimizing, we get to a place where every agent has minimized relative to what every other agent is doing. So that would say if we set the derivatives with respect to Z equal to 0 at every node's cost function, we get a system of linear equations, some very simple linear equations. And we see how naturally this fits into objects that we're familiar with from doing matrix computations for graphs, right? So the coefficients in this local optimality equation for node I can be naturally expressed in terms of the Laplacian matrix of the weighted graph. So imagine a matrix L whose ij entry is the negative of Wij, and whose diagonal entry is just the sum of all the Wij's. And that's, again, how we normally think of the weighted Laplacian for the graph. And that is the row of coefficients for this particular node I. As a result, these equilibrium equations, then they become the identity matrix, capturing this difference, plus the Laplacian, capturing the difference with all of your neighbors, times the vector Z of opinions should equal the vector of internal opinions. Or, taking inverses, we actually have this closed form expression for what Z is as a function of the innate opinions. Right, so we could see this equilibrium Z as varying, for example, depending on S, right? If I change S, I'll change Z. Similarly, if I change L, if I change the graph topology, I'll change Z. And so this is a model in which, very elegantly, you can sort of probe the sensitivity of Z, the observed heterogeneity of opinions that we see, the sensitivity of it to parameters that we're choosing for the problems, such as edge weights in L or innate opinions in S. There are some other interesting facts about the model. It's sort of, the tractability here means you can make a lot of interesting connections. I'll just mention two as a way of just getting sort of oriented around this. The first is a very elegant, very appealing random walk interpretation of all of these numbers, these ZIs. So rather than think of this as repeated cost minimization or repeated averaging, there's a completely different way that you could get these same equilibrium numbers, and this comes from a 2013 paper of Gionis, Terzi, and Saparis. Imagine that I were executing a random walk on these circular nodes, the ones with expressed opinions, and I could either walk to another circular node, or occasionally, if I randomly choose this link, I go to one of the squares. Now the squares are anchored to the values that they have. And what I'm interested in is the expected value of the square that I reach when I run this random walk, okay? You know, so for example, this node V, if it starts the random walk, it might go immediately here and pick up a half, or it might go in either direction. Well, if it gets here, it might pick up the 0, it might come back, and then just keep iterating. By symmetry, you would be correct in suspecting that the expected value of what you end up reaching in a square is 1/2. Recursively, that says, okay, so this node either goes right to 0, or it goes here, in which case it might go here, might go on to here, might do a lot of things. But since we've already decided that the expected value conditional on reaching here is 1/2, the expected value here is 1/4. Similarly, this is 3/4. And in arbitrary graphs, it's actually possible to work out that this is describing actually the same set of numbers. So this is yet another way to think about what these numbers are. It's the expected value you reach when you randomly walk according to edge weights. There's another interesting thing going on here, which is I've been talking about this cost function, right? This is the internal tension that node I feels with respect to their own internal opinions and with respect to divergences from neighbors. You could ask the social welfare question. What if I wanted to find the set of Z's such that when I summed all the CIs, I had as low a value as possible, right? That would essentially be the social welfare of the system, be the sum of all the ZI, of all the cost functions CI. The equilibrium is not what minimizes that. It's actually the thing on the right would minimize the sum of the cost functions. Why is that? Well, each node is locally optimizing, true. But if you think about it, from the point of view of social welfare, the stress along this edge is only counted once from the node, in this case from node U. The stress on this edge is counted twice, once from in U's cost function, but also once in V's cost function. So it says actually at optimality, we should not put equal stress on those two edges. We actually put more stress here and less stress here because this one's being multiplied by 2, it's contributing twice. And if you do that, it says you should nudge these values inward to make them 1/3 and 2/3. And in fact, in this case, right, so we see the social cost then becomes, if you do a bunch of little calculations here, 1/3, whereas the cost at equilibrium is 3/8. So the ratio between the equilibrium cost and the social cost is 3/8 over 3/9, or in other words, 9/8. An interesting fact about this model actually is that 9/8 is a relatively small gap, and that's actually as large a gap as you can get in any graph. If I were to ask the extremal question, over all possible graph topologies, how large can I make the gap ratio between the cost of equilibrium and the social optimum? It turns out the two are never far apart. There's at most a 9/8 ratio between them obtained by the 3-node path. Okay. Again, all of these are some worked examples with this model, just to get a sense of how it's functioning and the kinds of things you can do with it. If people did have questions, I'm happy to take any questions right now.
Any questions? If you have questions, please unmute yourself and feel free to ask.
I have a question. Hey, so John, so your second explanation about how to get the equilibrium point value is the average value like one node have seen when the node doing a random walk. So I'm thinking this may be explained as that value is what I think other people will think on this topic. And the first explanation is that's my opinion I expressed to the public. So it seems like explain like what I tell other people is what I believe other people think. Is there any like evidence like this actually is true, or like there's some tendency of people doing that? So I'm not saying what I really believe. I tell people what I believe other people believe.
Yeah, it's a very good question, and right, and there's in a sense a large area of empirical work that does this both both in practice, looking at found data out in the wild, out on the internet, and also in controlled lab studies, right? So for example, in extreme versions of these lab studies, I can bring people into a lab. I, as the experimenter, might have some confederates. I ask people to do some very simple estimation task, right? In a sense, the most famous of these is Solomon Asch's experiments from the late 1950s, where I simply ask people to decide which of these lines is longer. My confederates all say the wrong thing, and then it comes to you, and the question is, what are you willing to say, or what are you going to say in response to that? And these are, of course, set up to be extremely stark, where there's very little debate about the facts, and yet there's some social pressure to say what you believe everyone else seems to think. And so there definitely is a long line of empirical work that begins with that. There's also, this shows up in other estimation contexts, right? So there's a fact which has some amount of empirical support. I would say it's still in a sense a contested fact, that if I ask, for example, someone, who do you plan to vote for? That's a different question from asking who do you think is going to win the election, or who do your friends think they and often if you ask people who do you think is going to win the election, I'll actually ultimately be able to make a better prediction than if I ask who are you going to vote for, which, and on one level makes intuitive sense, on the other hand has a certain paradoxical flavor to it, because after all, the election is by definition determined by who everybody voted for. So you would think that randomly sampling and asking who are you going to vote for has to be the best prediction of that, and yet often you can phrase the question in terms of reference to others to sometimes elicit more accurate information. So I think there are a lot of interesting cases of this. I would say this dynamics of I'm going to say what I think everyone else thinks. At some level, that more exactly describes the de Groot model, where I'm simply trying to sort of fit at the average of my neighbors. Essentially, the Friedkin-Johnson model is saying I'm going to do that, but in the process, I'm going to feel this quadratic stress from deviating from somehow what I believe to be true, and so I'm going to do something that sort of balances between those sources of stress. Yeah.
Okay. Thanks a lot.
Sure. Other questions?
I think there is also another interpretation for this. I think you can also view the opinion that's reached as a convex combination of the initial opinions, where the convex combination is sort of the probability that the first node that you hit on a random walk is a particular node. I mean, and it's a convex combination of using those probabilities. Yeah. So that's another interpretation. Yeah.
That's a nice. Yeah. That's another nice interpretation, right? And the first node you hit might be yourself, so that includes that. But it's this. I think that's and in a way that interpretation, that the opinion that you're going to express is going to be this weighted sum based on these sort of terms based on multi-step paths, is a nice way to sort of derive a kind of network influence that each node has on you, even when they're not adjacent to you. So yeah, I think that's a very nice way to look at it. Yeah. Great. Okay.
John,
yep.
This is Shankar Shastri. Just about this last theorem, what's the technology that goes into that 9/8 on any graph into proving?
Yeah. So right. So I didn't. Yeah. So this one, actually, a theorem I'm going to prove in a couple slides will use some similar arguments, but effectively, you could think of, so the equilibrium equations are these. The social cost is optimizing something else, which effectively has a factor of 2. And so, because the edges each appear twice. And so that becomes, right, each of these is evaluated using a quadratic form, because if I have some vector z and I want to figure out what's the quadratic stress on all the edges, it's going to look like z transpose times Laplacian times z. And I'll write some of this down in a couple of slides. And so the local equilibrium is determined by one coefficient matrix, I plus L inverse. The social cost minimization determined by another one, which has a 2 on the Laplacian. And I'm now looking at basically the ratio of 2 quadratic forms. And so I say, here are these 2 quadratic forms. Where does one exceed the other by as much as possible? We find the axis where that happens and we derive that. Yeah, thanks. That's a great question. Any other questions, people?
Sorry, is a type of consensus that agents get when we actually apply a distributed consensus on them equal to the consensus, to a central consensus with a, for example, server that is manipulating them?
Yeah, it's it would depend on the specifics, of course. So one thing that's happening here is that, you know, and actually as Shrikant was observing, because even in the group model without internal opinions, you know, because we're getting nodes that are going to show up earlier on more walks through the graph, essentially, are going to have their opinion weighted more highly. The topology under which these nodes are connected is going to determine something about the consensus that's reached. And if I imagine something which tries to elicit values from each node and then do some centralized computation, it may not be subject to the particular topology in which they were connected. So you could see that as another sort of way in which what this model is trying to get at is how do the possibly almost accidental particularities of how these nodes were linked together determine the consensus that they arrive at? How might it have been different if they had been connected in some other way?
Thanks.
Any other? These are all great questions. So happy to take it.
No other question. Maybe we can proceed. Yeah.
All right. I'll move ahead. So let's talk about interventions in the network. So far we've been talking about this as an organic process that just unfolds, and we watch it unfold, and we draw some conclusions. But there are lots of cases where we might want to intervene for either, you know, purposes that are aligned with the goals of the participants in the network, or possibly that are misaligned or even antagonistic to the people who are in the network. What are some of these examples? We might, for example, want to lobby certain people, anchor their opinions at some high number, and then try to raise all the numbers as high as possible. As in this work I mentioned earlier with the random walk interpretation, was using that random walk interpretation in part as a way of thinking about this particular question. How would I intervene to raise values as efficiently as possible? We could do this in a few ways. We could do it by actually changing the values of the opinions. We could do it by changing how strongly you rely on your own internal opinion, right? As nodes rely less on their internal opinion, they begin to sort of float more freely in the rest of the network. You could obviously also change the graph structure, which is something that David Bindel and Segal and I did as part of the paper where we proved this 9/8 bound. And you know, there are a number of objective functions that we might have. Let me sort of classify them almost as sort of self-interested, altruistic, or antagonistic. The self-interested one might be to say, I have a particular opinion I want to have as the outcome. I'm going to try shifting opinions to get the consensus or to get as many nodes as possible to arrive as close to that as possible. I might have altruistic goals, such as in this work of Musko and Tsurakakis, where I'd like to just reduce the disagreement as much as possible. And how should I do that? By injecting as little intervention as possible into the network. I'm going to talk here for a few slides about some work that Jason Gaitandi and Eva Tardos and I did this past year on a question that obviously is sort of very much in the moment. It's similar to motivations in this nice recent paper of Chen and Ra is also from this year, and that's the goal of creating disagreement, right? And if we think about this in the spirit of what's often called offensive information warfare, what Claire Wardle in some of her recent writing has described as information disorder, the goal might be that of an adversary who, rather than trying to advance any specific opinion, is actually simply trying to increase discord in the network, right? They would simply like to increase contentiousness. If necessary, they'll take both sides of a very public argument if that causes polarization to increase. In some of the, and again, I recommend Claire Wardle is one person who's quite interesting to read on this topic. You know, so for example, one way she describes these approaches is that, you know, as a key strategy to spread as many conflicting messages as possible to persuade the audience that there are too many versions of events to find the truth, right? So to sort of deliberately create this giant heterogeneity. This quote is, we're not going to implement directly in our model because our model is in the end one-dimensional, and this quote hints at something kind of multi-dimensional potentially, but it gets the idea that I may not have any particular opinion as my goal. I literally want discord. And this is, again, something that's sort of made its way into policy circles, both the question of how do we safeguard against some of these, as well as obviously the question of, you know, sort of what the infrastructure is that makes these more or less possible. So what would that look like in our model if our goal was to advance disagreement? Let me describe a scenario. It's a simplified scenario, and this is one that's in the model from the work that Jason Kaitandi and Avatarish and I did. The work of Chen and Roz takes a different modeling approach to this. So this is designed to be very simple to sort of make the point that I'd sort of like to arrive at. Imagine that we start with a network that has complete agreement, right? There is no controversy in this network. There is no polarization. Every node is rooted at initial opinion 0. An adversary comes along and it has this budget of R, and it's able to introduce perturbations to the internal opinions, right? So the adversary might come, and if it has a budget of, again, for reasons of, I'm going to try to make this model as tractable as possible. Let's imagine it's a quadratic budget, right? So here the budget, you know, it had enough to spend X and on each of these nodes, and so it separates them, thereby creating spread in the opinions. And the adversary's goal is to maximize the disagreement in the network. Okay, so that's what we're going to be. That's what we're going to be considering. The adversary isn't really concerned with which opinions are reached. They just want to create as much tension along the edges as possible with very limited intervention. And again, we can sort of think about mechanisms by which intervening on internal opinions makes sense, right? There's the idea that these might be fixed information sources that this person is privately relying on. So if I can change those information sources, I can get this person to be anchored on something else. Okay, so this turns out to have an interesting solution, and it's sort of similar to some of the kinds of optimizations that we did in thinking about the 9/8 result as related to Shankar's question. Again, so this sum of quadratics is really just this quadratic form Z transpose LZ, so that's good. Z is I plus L inverse times S, as we decided earlier. So in terms of the initial opinions, which the adversary is intervening on, it's this other quadratic form, S transpose I plus L inverse L, I plus L, S. I'll mention that actually we might be interested in sort of a parametric form of this problem, right? We could ask how since the adversary is intervening on the internal opinions, and those are transmitted into the network across these edges, we might also be interested in a parametric version where the weights on the links in the real graph are scaled by some number alpha, okay? So that's basically showing the relative strength of the internal opinions to the neighboring opinions, all right? So in addition to thinking about this problem in general, I'll also think about how the adversary's solution varies as I change alpha, right? So large alpha, the network is basically a giant averaging mechanism because there's high weight on the graph edges. When alpha is very small, the network is mainly a mechanism for people to simply say their internal opinion and compare them to their neighbors because the network does very little averaging, although we're still summing over the edge, okay? All right, so how should we solve this optimization problem? Well, it's a quadratic form. All of these matrices are simultaneously diagonalizable. So they have a common set of eigenvectors, W1 to Wn. And let's index them in increasing order of the eigenvalues of the Laplacian, lambda 1, which is 0, lambda 2, all the way up to lambda n. Now, because everything is sort of simultaneously diagonalizable, the eigenvalues of this matrix, which we can sort of think of as L over 1 plus L squared, are indeed lambda over 1 plus lambda squared. And that tells us actually how to do the optimization, which is that the perturbation of S, right? So what the adversary injects, it's going to basically be multiplied, right? Its projection onto each eigenvector will then be multiplied by this coefficient. And so therefore, it should put all of its energy, all of its efforts on the eigenvector that maximizes the largest of these multipliers. Right? Because if we think of its perturbation as in the basis of the eigenvectors, the one where its budget will be used the most effectively is the one where this ratio is as large as possible. So how do we make that ratio as large as possible? Well, this function, x over 1 plus x squared, which is what the eigenvalue is going to pass through, looks like this on this plot, right? So if you imagine we take the eigenvalues of the Laplacian, lambda I, according to the ordering in the original Laplacian, and we sort them, and then we look at them along this curve, these are the eigenvalues in the adversary's optimization problem, in this I plus L inverse L, I plus L. Okay, it has a global maximum at x equals 1, where it takes the value 1/4. And so it says you should align the perturbation S with the eigenvector Wi, where lambda I is closest to the peak. Right? So in this case, you would, if this is the first eigenvector, second, third, fourth, you would, the adversary would simply align with the third eigenvector because that's the one that's at the peak. Now, here's what's interesting is let's think about the parametric version of this problem, because it gives us some insight into what's actually going on. So again, as we scale the weights in the graph, right, your connection to your internal opinion is fixed, right? Large values of alpha means the network is playing a huge role. As alpha shrinks, the network is playing a weak role, though it's still there to measure the disagreement. So large alpha, all the eigenvalues get scaled up. It looks like this. And so you should align, the adversary should align their perturbation with eigenvector number 2 when alpha is large. Okay. Now we increase alpha. And you know, if you've ever played with one of these toys where you slide beads along a wire, we see these beads are going to slide along this wire as we increase alpha, right? So they go along, they go over the peak. Now it should align with the 3rd eigenvector, and they keep going. They fall over the peak, and now it should align with the 4th eigenvector because it's the highest. So this funny thing happens actually. As we vary alpha, the optimum sort of picks its way through each eigenvector, right? One at a time, it's being aligned with each of the eigenvectors of the Laplacian. And that is a compact description of the adversary's optimal strategy as we vary multiplicatively the strengths on the edges in the network. So let's step back and, so when Jason, Ava, and I saw this, we sort of wanted to step back and we wanted to say, what does this mean? Because, you know, if you work with graphs and with their spectra, you work with their eigenvalues and eigenvectors, you know, you see lots of information that you can get from the extreme eigenvalues and eigenvectors, the smallest, the largest. But this is an optimization problem where every single eigenvector in the entire spectrum is actually playing a role in the optimization as we vary the edge weights. And as you think about it, so the first thing to note is simply, and certainly in my experience, those problems are rare. It's not that we can't make them up, but it's rare to find a natural problem where the entire spectrum jumps out at you quite so naturally. But there is something intuitive about it. And let me tell you why I see something intuitive. So if we think about the case of large alpha, which means the edge weights in the graph are very, very strong. They do a lot of averaging. Then we should align with an eigenvector associated with a small eigenvalue. And we know that from spectral graph theory, small eigenvalues tend to govern the behavior of sparse cuts in the graph, right? Sparse cuts like this one. On the other hand, when alpha is very small, so the network edges are very thin, they're very weak. And in some sense, people just express their opinions and we just compare them, but very little averaging happens. Then the large eigenvalues, then we should align with an eigenvector associated with a large eigenvalue. And those we know tend to govern the behavior of max cuts, right? So sparse cuts this way, max cuts that way. This actually makes some sense. If you just think intuitively, let's take away all of the calculations and just ask, intuitively, what is the adversary supposed to be doing here? Well, for large alpha, the adversary's problem is that if they inject a perturbation into the graph, alpha is very large, so a lot of averaging is happening. So the perturbation they introduce is just going to be averaged away, and all of their effort's going to be wasted. So if they want to keep that from happening, they should perturb this side of the sparse cut positively and this side negatively. And relatively little averaging will happen because there's only these two edges crossing the cut. So for large alpha, they should align with the sparse cut. In other words, align with the small eigenvector. Now, when alpha is very small, very little averaging is happening, but there's still this discord across the edges. So now the adversary should do the opposite. It should bring all that conflict to the fore, right? It might as well put +1s above the red line, -1s below the red line. There's going to be a huge amount of quadratic tension across these edges, and it won't get averaged away because alpha is so small. So you can see actually that as the weights on the edges change continuously, the adversary strategy literally does tilt from focusing on the sparse cuts to focusing on the max cuts. But it does it not really in a discrete graph theoretic sense, but in the spectrum of the graph, okay? And in some sense, right, the point is, and this is really sort of why the whole spectrum is showing up, that the network in the end is actually serving two purposes. It's being used to measure the discord, being used to measure the conflict, and it's also being used to average it away. And as a result, we see this phenomenon happening. This is another good moment to take questions. It's been another 15 minutes if people had questions they wanted to ask about this.
Questions?
So John, is there a discrete version of the problem where suppose you have two extreme types of opinions, 0 and 1, and the question might be, how many of these people you need to introduce to influence so that they change their opinion either to zeros or 1. And let's say you don't want to do this and you only want to do, I mean, the budget I'm thinking of would be maybe 5 people you want to select and you want to make them zeros and 1s. And then, So what, can this be applied to that? Yeah.
Yes, that's a nice question. And actually that gets to something I was mentioning a couple more slides. So this concurrent paper of Chen and Roz that looked at creating conflict adopts this sort of discrete constraint. They say, what if the adversary's budget is that it can pin K people's opinions at some desired value, and then how should we use that to sort of pull the network into as much conflict as possible? And so, and there are, in our paper, we talk a bit about how you can sort of use the spectral interpretation to find some connections between these two formulations of the problem. Essentially sort of doing some kind of a thing that imposes a sparsity constraint in the non-zero patterns.
Thanks.
Yeah, good question.
Shankar again. So terrific. You know, this lot. Can you add color to the very last thing you said before you threw it over for questions? You said as you change alpha, doesn't, you know, this was the interpretation for large and small alpha in terms of the graph cards. But then you said it doesn't do so in such a discrete fashion. It does it in the sense of the eigenvectors. So what about all the intermediate cases between the max cut and sparse cut?
Right. It's a great question, because I will admit to not having a sort of fully worked out intuition for what's happening in the middle. And you know, in part, it's really, my intuition is so grounded in extreme eigenvalues, you know, the smallest ones and the largest ones, that, you know, I've spent comparatively little time thinking about what's happening in the middle. But effectively, what's happening, right? What's happening here somehow is that, you know, we start with, say, alpha very large, and we run a sparse cut, and now alpha begins decreasing. So it's sort of safer to begin introducing more conflict. And the first thing it jumps to is, in the sense, the next of the eigenvectors. Now, we know from some results, like results of Luca Trevisan and others, that you know, what you can get actually is that it's not just the most extreme eigenvalue that governs the sparse cut, but that, you know, the smallest k can give you some information about sort of k-way sparse cuts. And so it's, in a sense, pivoting from one very sparse cut to a slightly less sparse cut. And in some sense, I think it's sort of working its way through those. But it's a good question. Yeah.
Thanks.
Sure.
Hey,
Thanks.
So
hey.
So I have a question actually related to what Srikant asked. So if we change the budget from like 2 norm to 1 norm, what do we have in that case?
Yeah, it's an interesting question. So you asked this question. It doesn't have quite the same nice interpretation here, because, right, there's still a convex feasible region. We lose the connection to the spectrum as such, but we still have some ability to work in the convex feasible region. So I think it's an interesting question to sort of talk about what the sort of what the most succinct way is to describe how the optimization happens parametrically across alpha in that case.
Okay, thanks.
I have one question. Yeah. So in the social network, the weight, you know, the neighbor's weight is somewhat volatile. We do not know the exact value of the weight, but the weight influences the eigenvalue, right?
Yeah.
So in reality, how do we know the weight?
Yeah, it's a good question. Like, I mean, I would say in general, and this sort of bookends my point at early on in the talk, that in the end, these are theoretical models, of course. And so I think one of the interesting challenges in this whole area, which, you know, I think will come out in a number of the talks that you'll be seeing, is how to align some of what we're seeing in the theoretical models with what we can actually determine empirically. So, you know, if I think about sort of work on the sociological side in the diffusion of innovations, you know, a lot of that is looking at sort of trying to find reasonable quantitative measures of tie strength, and also the kind of multidimensional nature of tie strength, right? There's some people from whom I'll get new information, some people who I'll trust, some people I'll turn to for help. And so all of these are sort of, as I watch people's behavior, ways of estimating different forms of weight. And I think, you know, a very interesting question is sort of how to sort of take those multiplex, notions of weight and think about sort of how they align with some of the questions here. And I think that's a very important question at this boundary between the theoretical and empirical work here that, again, hopefully I think work in this space will continue making progress.
Okay, thank you. Yeah.
Right, yeah, thanks. Yeah, it's a very important question. Any other, otherwise let me say a bit about this third part, which is, let's actually go back to this multi-step path about the brilliant response from the millennial to Matt Taibbi's displeasure over Rolling Stone's endorsement of Hillary Clinton. Let me propose a second interpretation, also valid. I mean, in the end, this is just, a page on the web, and so we can impart a lot of interpretations to it, all of which are, I think, informative. Rather than thinking about the opinions at the nodes, we could think about the polarities on the edges. Because in a way, an endorsement certainly indicates that this link is somehow, in some, however we want to mathematically model it, there's something sort of positive about this link. And Matt Taibbi expressing displeasure with his employer, Rolling Stone, somehow has a negative. This millennial with the brilliant response, we're inferring from the headline that this is also negative, and the fact they call it brilliant means this is positive. And of course, in your mind, you begin making other sort of inferences, like the fact that this millennial was somehow rebutting this criticism means maybe the millennial is aligned with Rolling Stone and maybe even aligned with Hillary Clinton. The fact that they're supporting it means maybe they also are aligned with these people. You sort of get this kind of 4 against 1 picture here, right? That these 4 nodes are kind of all on the same team with this person. And you're doing all this by using sort of intuitive inferences about what happens with positives and negatives edges that would be sort of useful to write down precisely, right? We do this in a lot of contexts in the online world, right? We have cases where we say, I agree with you. We say, I find your opinion helpful. I trust you. I vote in favor of admitting you into the community. It's entirely believable that we might apply different theories to different of these link interpretations. But I want to sort of talk here about one that's fundamentally about agreement and disagreement, or about friend-enemy relations. And that's the theory of structural balance, which is, again, one of the sort of oldest and most classical mathematical theories in sociology and social psychology. So this is based on the kind of, it sort of starts from the kind of reasoning that we do in analyzing this Rolling Stone endorsement of Hillary Clinton. It starts from these proverbs that the friend of my friend is my friend, the enemy of my friend is my enemy, friend of mine is my enemy, so forth, right? You'll notice actually, normally we don't really talk about the combinatorics of proverbs, but let me try here. There are sort of 3 slots in this proverb to put the word friend or enemy. So 2 times 2 times 2, there are 8 possible proverbs you could write, but some of them are kind of weird. Like the friend of my friend is my enemy would be kind of weird. Like I don't think any of us believes that. What's written down here is the 4 that arguably make sense, that feel correct to us. And they're all the ones where the word friend occurs an odd number of times. And there's a graph theoretic picture of this that makes it clear why all this is happening, which is these are all statements about 3 people, let's call them A, B, and C, and whether they're friends or enemies with each other. And starting with the work of Fritz Heider, put on a mathematical basis by Cartwright and Harari in the 1950s, you can look for signings of triangles that are consistent with this logic. So when it's consistent with this logic of friend-enemy relations, we call those triangles balanced. And when it's inconsistent, we call it unbalanced. So for example, 3 pluses is viewed as very stable. There's no violations of the maxims of friend and enemy relations. We call that balanced. Similarly, 2 friends who have a common enemy is viewed as stable. That's balanced. Whereas if A is friends with B and C, but they're enemies with each other, there's some psychological stress there, right? Because A would prefer that B and C reconciled with each other because there's tension there, and they're both friends of A's. B is, presumably constantly trying to get A to side with them against C and turn this plus to a minus. C is doing the same thing. So there's tension that has to get worked out in this triangle. It is not balanced. And similarly, 3 mutual enemies, there are different theories about this, but we'll sort of follow a theory that says in these kinds of situations, when the stakes are high and everyone knows each other, there'll be an incentive for the 2 of these people who get along the least badly to team up with each other against the 3rd as a mutual enemy. And so there's a again, tension here that has to get worked out. There's a famous theorem in this area, and it basically relates what's going on at this local level, at the level of 3, to what's going on in complete graphs on n nodes, right? So imagine I take a complete graph on n nodes, and I put a sign plus or minus on each link, and I then ask that every triangle in it be balanced, right? So every triple of people is going to try to obey this logic in their own three-way relationships. But I'm in an n-node complete graph, so those triangles have to all fit together with their pluses and minuses in a way to get this to all work out. So how do we do that? Well, if we made everything plus, we could certainly get everything to work out. Then we just have all plus triangles here. Similarly, if we had two sets, everyone inside set X were mutual friends, everyone inside set Y is mutual friends, and every edge between here is negative, then every triangle is either entirely on this side with all pluses, or entirely on this side with all pluses, or it has two nodes on one side, one node on the other. It's a 1 plus 2 minuses. It's two friends with a common enemy. So any structure like this will indeed have every triangle be balanced. And the elegant theorem of Cartwright and Harari is the converse, that if all triangles in a signed complete graph are balanced, then the nodes can be partitioned into two sets of mutual friends, one possibly empty, with all negative edges in between them, right? In a sense, this is actually one of my favorite examples of a sort of micro-macro link in the mathematical social sciences. That kind of local implies global, right? It says, let's think at the global level about polarization, right? Two groups of opposed sets of allies. Or let's think locally about sets of three people trying to establish psychological balance in their relationships. These two are the same thing. We can actually link the purely local with the purely global. But one interesting open question here, which is what I'll sort of spend a couple minutes on and then end, is that elegant as this theorem is, it's a theorem about statics with no dynamics. If I start with a disordered complete graph where people are friends or enemies, a bunch of triangles are unbalanced, can I describe a plausible dynamics that leads to this global structure, this perfectly balanced structure? I should say, ultimately, this is a theory of polarization, right? It's not clear that this perfectly balanced structure is something that we should be rooting for. It means we have this intractable conflict, but it is the end point of working out all of the psychological tension in all of these triangles. And what is the dynamics that might lead to that? So I'll just point to two things, and I mentioned these. They're actually from some number of years ago, and I've been coming back to them because I'm looking at some of the work we've been doing on creating polarization at the node level opinions, and it feels like there are these connections to the edge level. Discrete dynamics are challenging here, right? I could say discrete dynamics means A and B have to decide how to update the sign on their edge. They're going to pick the sign that's going to make as many triangles that they're in as balanced as many as possible balanced. This is a discrete local search process, but it has numerous local optima the system can get trapped in. It certainly does not end up reliably getting to a completely balanced state. There's a continuous dynamics, however, that was proposed by Kulikovsky et al., in which with Seth Marvel, Bobby Kleinberg, and Steve Strogatz, we were able to analyze, that says we can actually get a reasonable dynamics by working in continuous time. And so imagine that rather than just plus minus, I actually have real numbers on these edges. So the edge weight between nodes I and j is a real number xij. And it's going to evolve according to this very natural differential equation. The rate of change of xij is going to be based on how they feel about mutual third parties, right? So for every third node k, I'll look at the product of their relation. If they're both positive toward them, or if they're both negative toward them, I get a positive product, and this number goes up. They get more friendly because they feel the same about this third party. That's structural balance. If one is positive and one is negative, that's an unbalanced situation. The product's negative, and it goes down. So basically, there's now a superposition of forces on this edge, some pushing it up, some pushing it down. I get a system of differential equations. I mean, it's an elaborate system of differential equations, but it turns out to have a nice matrix interpretation, not unlike some of the spectral analyses that came up in the earlier parts of the talk, although it's now operating on edges, right? There are no node level opinions here. There's really just the relation between I and j is a thing unto itself. And what we're able to show is that if I start with generic initial conditions and I normalize the system as it goes, because there's actually a system that actually blows up in finite time, the system converges in finite time to a solution xij equals yi times yj for numbers now on the nodes. Okay, so as the system time evolves, these differential equations, I get to a situation where xij is just a product of yi times yj. And you now see how that leads to the Cartwright-Harari kind of balanced two opposing forces, because all the nodes I where yi is positive form one side, and all the nodes j where yj is negative form the other side. And the signs of the edges can be totally read off from that, right? The product of two positive numbers on one side, the product of two negative numbers on the other side, and two nodes that go across the divide is a positive times a negative, they'll have a negative relation. And so it turned out that working in continuous time, there's this nice way to disentangle this whole system. With more time, I'd be happy to talk about sort of how this differential equation sort of works itself out. And in fact, the connection to spectral calculations that again, were striking for me in that this was work I'd done some time ago, but the spectral connection felt very familiar relative to this recent work that we've been doing. And so I think there are some interesting potential connections there that I don't fully understand. So with that, I'll wrap up. We've talked about many different processes you can model with opinion dynamics. You can talk about interventions, you can talk about node and edge-based processes. Spectra of graphs obviously play a big role here. I think there are a number of interesting questions. Certainly the range of interventions is large. We can think about those. We can think about how they relate to actual empirical data we have about the effect of interventions on networks. And again, I think the theoretical empirical boundary in this area is quite rich. There's been a lot of work on it. I think there's a big opportunity there. The fact that we have this optimization problem in the middle third of the talk that involves the complete spectrum of the graph, I still find intriguing, and I think there's still more we can understand there. And finally, some of the things we're seeing now with node level opinion dynamics echo things about structural balance at the edge level, even though the types are different. One is about values on nodes, one's about values on edges. And I think trying to find sort of the deeper connections there is also going to be very interesting as we move forward, pursuing really both the theoretical and the empirical implications of this very important area. Thanks very much.
Thanks, John. It's a terrific talk. I know you have to rush to teach, so I don't want to hold you further. But again, thank you again. And
thanks very much. Thanks. And yeah, if people have questions, I'm happy to also take questions afterwards if you want to send an email. Yeah.
Sure. I mean, there are a few questions on the chat, but maybe I'll reserve them for you when you come back.
Sounds good. If you want to pass along one question, I think
Okay. So one quick question was that, can we retroactively determine alpha and the effectiveness of adversarial disruption?
Yeah, that's an interesting question. I think, so we speculate on this a bit in the paper that, you know, to the extent to it, so obviously alpha is somehow a statement about how powerful the social ties are relative to our own innate opinions. So, and so I think there are interesting questions there where we look at sort of how much social influence is needed. For example, in lab type studies to get people to abandon what are clearly sort of strongly held beliefs, even factual ones, right? Even experiments where I'm getting you to go against something you sort of factually believe. And so I think that's one way to probe it. I think it's also interesting to start asking about the ways in which the networks on which we are sharing information, such as on social media, are becoming sort of decoupled from the networks on which we're sort of feeling tension, right? So it could be that I go online, I read a lot of incendiary things, it moves my opinion. I then sort of bring those more extreme opinions to a friendship I have in the offline world, causing stress. And so the network on which the discord's being measured can sometimes diverge from the network on which the opinions are being formed. And I think that's also an interesting way to think about this contrast that we talk a bit about in the paper.
Thank you again.
All right.
We'll see you.
Thanks very much.